Good morning, everyone. It's the first thing in the morning right now, and we are getting started on Chapter 8. So let's get to the first lesson. It is 8.1 Sequences. Here we go. This chapter, we're going to talk about Indiana Jones a lot, and Indiana Jones was a creation of George Lucas, who was also responsible for the Star Wars stuff we did last chapter. And he's kind of an homage to the 1930s film serials and, kind of swashbuckling explorers that George Lucas grew up with. The first appearance would be in the 1981 film Raiders of the Lost Ark, where he is portrayed by Harrison Ford. Ford's kind of characterization of Indiana Jones was a big reason why a lot of people really enjoyed this. I really enjoyed this growing up. So the one we have here is from the very first film, where we have the archaeologist and his one-time girlfriend Marion Ravenwood, the daughter of Indiana's mentor Abner Ravenwood, in a 1936 Nepalese bar with a strikingly international clientele. That's really really specific, but attempting to win a contest by drinking quote-unquote grape juice. You know it wasn't grape juice. The contestants will drink from numbered bottles on the shelf, and which bottle will each contestant drink next? So, some unnamed Nepalese drinks bottles 4, 6, 8, and 10. What bottle will he drink next? Some unnamed German goes with log 2, log 6, log 18, and then Marion 4, negative 12, 36, negative 108, and yeah, that's kind of weird. So let's see. Let's construct that sequence of bottles by the Nepalese, and we'll call that braces Ni equals brace N1, N2, N3, etc. and brace. So you guys can stop calling them curly brackets. They're braces. Okay, N1. The first bottle that we drink is bottle 4. And then the Nepalese drinks 6, and then 8. And the next one would be 10, but look at this. They want the 10th one in this sequence. So you can keep on counting, or you can try to find a pattern here. And it looks like we're adding 2 every time we go down the line. So N2, we add plus 2. N3, we add plus 2 times 2. N4, we would add 3 times 2. So that means for N10, we should add 9 times 2. Four plus 9 times 2, that is 22. So the 10th round, we're going to be at bottle number 22. Can you think of an explicit formula for knowing which bottle was drunk by the Nepalese? Well, we started with the 4th bottle, and then we added the next number, or the index number, minus 1, n minus 1 multiplied by 2. These numbers here, the subscripts, we tend to call them index numbers. So here is a formula. Let's check and make sure. N1, that's going to be 4 plus 1 minus 1 times 2. That's 4. N3, that's going to be 4 plus 2 minus 1 times 2. Of course, I meant 3 minus 1 times 2. What is that? 4 plus 2 times 2, 4 plus 4, that's 8, and yeah, that tracks. And then, of course, N10 is going to be 4 plus 10 minus 1 times 2. And that's going to be, let's see, 9 times 2 is 18. 18 plus 4 is 22. So yeah, this seems to be a good pattern. Some of you might want to just simplify that, and you're going to get 2 plus 2n, but that's not really of any consequence. It's kind of the same formula, just algebraically different. Next, we have a definition for the recursive formula. So the recursive formula states the first term of the sequence and then the rule given for the next term given the previous term. So here we have the first term is 1, and then any term ni is equal to the previous term ni minus 1 plus 2. So we can try that with the Nepalese formula, with the Nepalese bottle system. So if n1 equals 4, then n2, that's going to equal n2 minus 1 plus 2, or n1 plus 2. n1 was 4, so that gives us 6. n3, that's going to be n3 minus 1 plus 2, which is n2 plus 2, or 8. And notice if I wanted to get to n10, that's going to be a very long crawl all the way 10 terms. There's no way to kind of shortcut. You need to do this sequentially. So what is the recursive formula that tells us which bottle Marian's going to drink from? Let's go back to Marian's sequence. What's nice about this is we get to think about sequences just from one term to the next rather than trying to get the entire thing. So if we go just from one to the next, how do we get from 4 to negative 12? Well, we could subtract 16, or we could multiply by negative 3. How do we get from negative 12 to 36? Well, we could have added, 48? Or we could multiply by negative 3. And already we see that this is probably the pattern because it's a repeat of things. How do we get from 36 to negative 108? Again, we multiply by negative 3. And you could probably sense that this is going to be a pattern involving multiplication because the differences here keep increasing. The difference between 4 and negative 12 is smaller. So the difference here between 2 and 3, where are we? Oh, I'm sorry. Between 3 and 4 is even bigger than the difference between 2 and 3. So when those differences increase like that, then we're probably going to start suspecting a multiplication pattern. Anyhow, let's get to this. The recursive formula for Marian. The first term was 4. And then to get to each term, we're going to take the previous term, and the shorthand for that is mi minus 1. And then we're going to multiply by a negative 3. So that is our recursive formula. Let's write it over here on the side. Okay, so next, let's write an explicit and general formula for the sequence of bottles drunk by the German. We're going to call that GI. Looking at the German sequence, we've got natural log of 2, natural log of 6, and natural log of 18. And if you just take a look, don't think about the natural log, but if you think about the 2, 6, and 18, there seems like there could be a pattern there. The difference between 2 and 6, let's write it over here. The difference between 2 and 6 is 4, and then the difference between 6 and 12, 6 and 18 is 12. So the difference between the numbers keeps on getting bigger. So maybe we should start looking at multiplication. From 2 to 6, we multiply by 3. From 6 to 18, we multiply by 3 as well. So that seems to be the pattern. Now, the pattern isn't in the natural log. The pattern is in the number that's inside the natural log. Now, the problem is we need to figure out how to multiply the number inside the natural log. So you may have to think about some properties of natural logs, what allows us to multiply inside, and it's actually going to be natural log of 2 plus the natural log of 3 is equal to the natural log of 2 plus the natural log of 3 is equal to the natural log of 2 times 3, or natural log of 6. Remember that property of natural logs where the natural log of a times b is equal to the natural log of a plus the natural log of b. So we kind of solved it here. To the first term we'll call g1. That's going to be equal to the natural log of 2. And then for each additional term, gi, that's going to be the previous term, gi minus 1, plus the natural log of 3. So it seems like it's a multiplication sequence, but it's actually an addition sequence. Interesting. So that's my recursive formula. My explicit formula is going to be the explicit formula that we use for any addition formula. We start off with the first term, natural log of 2, and then we add to it a multiplicity, n minus 1, of the common difference, which was natural log of 3. So this is going to be we used I, but any g is going to be natural log of 2 plus I minus 1 times natural log of 3. That is the common way that we usually do arithmetic sequences, which I guess we didn't know what it was called, but that's what it's called. If you want to simplify that, you can say this is natural log of 2 plus natural log of 3, or I multiplied by the natural log of 3 minus the natural log of 3. Or we can say this is equal to the natural log of 2/3 plus I multiplied by the natural log of 3. Okay, that's all of our natural log stuff for today. And sequences that are formed by adding constants, like this natural log of 3, we call that an arithmetic sequence. The constant that we keep adding is called the common difference. So in our case, the common difference is natural log 3. Sequences that are formed by multiplying are called geometric sequences. And a geometric sequence is like the sequence of Marion that we had here. And what we keep multiplying, that constant, that's called the common ratio. Probably the easier geometric sequence to think about would be the geometric sequence, the arithmetic sequence that's easiest to think about. That's probably going to be the one over here with the Nepalese. So for the Nepalese, this is a arithmetic sequence, and the common difference is a positive 2. So which sequences were arithmetic? That was NI and GI. And finally, which were geometric? That was MI. Now remember, we started off with the GI, the German sequence. We started off thinking that there was some kind of a multiplication at play. And there was some kind of multiplication at work here, but it was with the inside of the natural log, not the entire thing. Here's our important ideas. We've got a sequence is just an ordered list of numbers, such as sometimes we put that with just without the braces in it, but that's probably better with braces around that. S is 2, 5, 25 over 4, 125 over 4, etc., etc. The explicit rule is a formula or function that will output a specific element in the set. So if you want the 39th term of a sequence, you better have the explicit rule, because if you don't, then you're going to have to use a recursive rule, which means to find the 39th element, you're going to have to find the 38th, the 37th, the 36th, the 35th. There's no way to fast forward through the sequence. Here are the general forms for the arithmetic sequence. AI, or the explicit rule, AI is just some number. And, the explicit rule, AI is equal to A1 plus n minus 1 multiplied by the common difference. The recursive rule, AI is equal to some number, or A1 equals some number, and AI is AI minus 1 plus a difference. You need both. And you can imagine that many negligent students are going to forget A1. That's true also in the geometric recursive rule. Students will forget G1, and we have G for the recursive rule for a geometric sequence. We've got G1 has to be stated. I was going to say explicitly stated, but that's getting confusing. But that first term has to be stated, and then the rule to get to the next term is the previous term multiplied by the common ratio r. The explicit rule for a geometric sequence, which we didn't talk about, that's just the first term multiplied by the common ratio to the n minus 1 power. Now, arithmetic and geometric sequences are the only sequences that we're going to be really worried about in this section, but you need to know that there are more sequences that fall outside of arithmetic sequences and geometric sequences. So don't think that if you master these two sequences, that's all the sequences that are out there. There are plenty more. We just don't have the time to talk about it since this is a calculus course. Now, Part A, find the first 4 terms of the sequence and the 8th term of the sequence. We've got an equals n over n squared plus 1. So that's not that big a deal because we have the explicit rule. So the first 4 terms. Let's start off with A1 just to kind of demonstrate. A1 is going to be n, which is the index number, so 1 over 1 squared plus 1. That is 1/2. Let's look at A2. A2 is going to be equal to, well, now n equals 2. So we have 2 over 2 squared plus 1. So that's 2/5. 3 over 10 and 4 over 17 rounds out the first 4 terms. And then it says to find the 8th term. So A8, that's going to be equal to 8 on top of 8 squared plus 1, which is 65. So 8 over 65. Now part B, that's a recursive formula, -3 and 2 times bi minus 1 plus 1. So here, this doesn't look like either the geometric sequence nor the arithmetic sequence. So we're going to have to actually go down and do all of these. So let's start with the first one. B1, of course, is -3. B2 is going to be 2 times B1 plus 1. Well, B1 was -3. 2 times -3 is -6. -6 plus 1 is -5. So our first term in the sequence, let's get the brace down there, -3. Next term is -5. Next term after that, B3. That's going to be 2 multiplied by B2 plus 1. 2 times -5 is -10, plus 1 is -9. And then we keep on going. If you went all the way to the end here, you would have seen that B8 is equal to negative 257. So quite a lot. Now, for part 2, do we have an arithmetic geometric sequence or neither? Write a recursive rule and an explicit rule for each one. Part A, let's see, 1/3, 1/9, 1/27. Now, in my brain, I've been, trained myself to see this sequence, but I'm just the numerator is staying the same, but the denominator is the powers of 9 or the powers of 3, 3, 9, 27, 81. Once you see it and you know it, you can't really ignore it. So we seem to be multiplying by -3 here. So this looks geometric. And a good tip for you, whenever you write down one of these two sequences, you want to write down the first term. We'll call it A. A1 equals 1/3. And once you know what the ratio is, you want to write down the ratio. The ratio is -1/3. Now with those two numbers, we can figure out the explicit and recursive rule for every geometric sequence. For the explicit rule, an is equal to a1 multiplied by r to the n minus 1. Now at some point it becomes easier to write out an n than an I. So n is a common index used in sequences. So we're just going to go to an. It's kind of what I'm used to, more natural for me. Let's plug in the numbers. And that's kind of where most people stop. But, there is some algebra you can do here to simplify that a little bit. We can separate this -1/3 to the n minus 1 power and say that's -1/3 to the n multiplied by -1/3 to the -1. And we get negative of -3 to the n power. Next rule for that is the recursive rule or the recursive formula. So the recursive formula, we state the first term, which was 1/3, and then we state how to get to the next term given the previous term. So an, which is the next term, is an minus 1, which is the previous term, multiplied by -1/3. And the recursive rule is so much easier to write, less easy to actually work with. That takes care of part A. Let's look at part B. And let's look at the differences. -3 to -9, that's an +4. -9 to -5, that's also a +4. -5 to -1, that's also a +4. So it looks like we're just adding 4 to each of the previous terms. That tells me that we have an arithmetic sequence. Also tells me the first term a1 is -13 and the common difference is +4. The formula for the explicit rule of an arithmetic sequence is an equals a1 plus n minus 1 multiplied by d. Substitute numbers and then do a little bit of algebra. This algebra is a little bit less esoteric than the previous one. And we get an explicit formula an equals -17 plus 4n. Am I supposed to use a? No, you know what? Let's change this to b. Because, well, this is part B of the sequence, of the problem, that is. Okay, everything is in terms of b now because this is problem B. Let's look at the recursive formula. So the recursive formula, we state the first term of the sequence, which was -13, and then we say that each nth term is equal to the n minus 1th term plus a -4. And that's it. So this is a pretty gentle section. That was actually a lot of information, but none of that was too intense or intellectually challenging, I don't think. Get a hold of the vocabulary, get a hold of those, 4 formulas, 4, 1, 2, 3, yeah, four different formulas that you have, and then you should do pretty well here. All right, see you next time.